Alrighty, so this is the lab on density of a gas. Um, the purpose of this lab is simply to determine what the density of a gas is, which seems like a very simple kind of purpose, especially when compared to the lab we did on density of solids and density of liquids. In those two labs, what we were doing was measuring the densities of similar looking solids to compare them to see if they could be the same substance. And then with the liquids, we measured mass and volume and calculated density of two similar looking liquids in order to compare their densities to see if they could be the same. In this lab, we're not actually comparing different gases to each other. We're simply going through the process of how to actually create a gas, capture the gas, measure its mass and volume in order to then calculate density. The reason that we're doing this is because gases are very tricky. They're not easy to handle, and so measuring them is very challenging because you can't just grab some gas and put it on the balance, nor can you just grab some gas and measure its volume. So we have to kind of go about this in an indirect fashion. And so really the whole purpose of this lab is, how do we even approach this? And then in the end, we're going to look at the density of a gas and compare that to the densities of other states of matter in terms of densities of liquids and densities of solids to kind of get a feel for how each state of matter kind of lines up in terms of their densities. So that's kind of where we're going with all this. So because we have to measure this indirectly, the way we're going to measure the volume of a gas, so actually let's back up. We're going to create a gas in the first place so that we can measure it. And we've done part of, this is kind of like two labs in one that we've done before. We have an Alka-Seltzer on the balance, and we're going to use a whole Alka-Seltzer in this test tube of water to create the gas. We know from past experience that breaking the Alka-Seltzer and putting it in the test tube, the minute it hits the water, it creates lots of gas. As soon as we drop the Alka-Seltzer into the test tube, we're going to stopper it so that we can then purposefully transfer all that gas over here into this collection bottle. Now, we've done this setup before as well when we did the baking soda lab, because we set this up also in order to collect a gas. So what's going to happen is, as the gas travels through the delivery tube, it's going to displace the water in the bottle. So then we'll have created a gas and we'll have contained it over here in this bottle. So then the task becomes, how do I measure it? How do I measure its mass? How do I measure its volume? So the volume part's a little bit more straightforward. So what we did originally was figure out how much water fits into this bottle. So the starting volume of our bottle, it can hold 1,050 cubic centimeters of water. So that's how much water is in there at this moment. Now, once the gas is created and transferred to the bottle, it's going to push some of this water out. So we're not going to have a full 1,050 cubic centimeters of water when we're done. So what we'll do is, we'll have, we'll have a certain amount of gas in the bottle. We'll then remove the bottle from the tub, keeping our hand over it so none of the water gets out. And we're going to measure how much water is left over. So if I know how much I'm starting with, and then how much is left over, I can subtract those two to figure out the volume of the gas that we just produced. So that's how we're going to do the volume part. The mass part, we're going to be using what we know of the law of conservation of mass to figure out the mass of the gas. And we've done part of this before when we did the Alka-Seltzer lab in chapter 2. So what we're doing is we're going to get the starting mass of all of our stuff. We have our test tube, we have about 5 cubic centimeters of water, and we have a whole Alka-Seltzer. The starting mass of all that stuff is 44.762 grams. Now, we know, based on the law of conservation of mass, as long as it's a closed system, which it will be, that the mass should not change. So in the end, we should still have 44.762 grams of stuff. Now, the only difference is the gas that's created from this reaction is going to be over here. So we're going to have part of our mass here and part of our mass in the test tube, right? So what we're going to do then is get the mass of what's left over in the test tube at the end. However much that mass goes down, that's exactly equal to how much gas we transferred to this bottle. So again, we know that what we're starting with, the Alka-Seltzer and the water, that mass won't change, even during the chemical reaction between the Alka-Seltzer and the water. So that's going to react, and then we're purposely going to take the gas that it produces and put it here. So in the end, when we mass the test tube with the water and the leftover Alka-Seltzer, we're going to notice the mass goes down a little bit, and it's going to go down by exactly how much gas we moved over to this bottom. So when we're done, we're going to get the ending mass of the test tube and its contents, and we'll subtract the two, and that will tell us how much the mass of our gas is. Then we'll have our volume and our mass, and we can calculate the density. So that's in essence what we're doing. Again, it's a very indirect approach because when we're dealing with gases, they're tricky little guys, and we cannot do it directly, so we have to do it indirectly. And so that's basically what we're going to be doing today. So, having said that, we're ready to actually get this thing going. So I've got my test tube. I'm going to have to, let me walk around over here. I'm going to have to break this Alka-Seltzer in half because it won't fit into the test tube when it's full. But I've got to be ready so that as soon as I drop it in the water, I stop it immediately. And, oh shoot, I dropped a piece. That's going to mess it up. Well, if our results are off, we'll know why. Hopefully it won't be too far off. So you can see right off the bat, actually if I can stand over here again, so you can see the backdrop of this a little bit. If I stand here, yeah, there we go. You can see just how much gas is being produced. I colored the water red so it'd be easier to see on the video, but it produces gas very, very quickly. And if you look at the test tube itself, you can see it's very fizzy and foamy, producing lots and lots of gas. And as it's doing so, the gas that we want to measure is being transferred over here so that we have it and it's contained and we can see it, sort of, in an indirect kind of way, and then hopefully get a good measurement at the end. This is the part of the video where you can fast forward because we're going to need to wait. The book says 10 minutes. I might wait about 8 minutes. But we've got to wait a little while for the reaction to finish. If we don't wait long enough, then we're going to get inaccurate measurements at the end. So we want to wait long enough. We want to make sure that the reaction is at least 90 to 95% complete before we take our numbers. So I'm going to let this sit. The video will keep recording, so what you can do is now fast forward until the part where I'm going to take the measurements at the end. So I'll be back in a couple minutes. reaction, about as close as we're going to get. So now we're at the part where we've collected our gas, and we need to measure our ending volume and our ending mass, so then we can calculate the mass of the gas, the volume of the gas, and then its density. So let's see. Let's start with the volume of the bottle. So we want to very carefully remove the delivery tube first, out of here. And we don't want to let any of the water out of the bottle, because that would be misleading in terms of our final results if we let any of the water out, because we want to know exactly how much is left, so that we know exactly how much was pushed out of the bottle, so that we know exactly how much gas was produced. So here's how much is left. Where are we here? So you can see it. That's how much, you can stand and see it probably better. From about here to here, that's how much gas was produced. So we're going to figure out how much water is left over. I'm going to use 100 milliliter bottle, 100 milliliter graduated cylinder to be more precise, and measure 100 at a time, so I can figure out how much. That went a little over, so we'll some of that back. This is a little tedious, but that's okay. It'll be worth it in the end, so that's 100. Oh, very good. That's 200. Okay, where I'm at. 500. Okay. 733 is how much water was left over. 733. So let me get my trusty little calculator here to ensure I do the math correctly. So I started with 1,050 cubic centimeters of water. I had 733 left over, which means I had produced 317 cubic centimeters of gas. So there's my volume numbers. The bottle held 1,050 to start with. At the end, there was only 733 left in the bottle, which means 317 cubic centimeters of gas was produced. Okay, now let's do our mass. Alrighty. Now the reason we have the rubber band on there is to keep the test tube from falling over. And again, as long as we have that on there at the beginning and at the end, we're good to go. Okay, so let's see. point, oh, for heaven's sakes, I just touched the balance. That's annoying. Let's let it settle down. Settle down. Okay. 44.123. 44.123. 44.123. Let me just double check that. 44.123. Okie dokie. So that's my ending mass. Now remember, the mass shouldn't change. The only reason it does is because we took the gas from the test tube that was created in the test tube and we moved it and put it into that water bottle. So the difference between the starting and ending mass tells us exactly how much gas we moved and put into that bottle. So let's do the math and let's just see how good I am, because who knows how close my numbers are going to be. So this tells me that my mass was 0.639 grams. Okay, so through all of that indirect measuring, we found the volume of our gas was 317 cubic centimeters. The mass of our gas was 0.639 grams. And so we're going to calculate the density, which is mass divided by volume. So 0.639 divided by 317. Oh, wow, not too bad. I did pretty good. All right, so in terms of using significant digits, I should have 3, so 0.00202. 0.00202. And that's going to be grams per cubic centimeter. Okay, so based on the measurements we just did here, you can see my math up here. Density is mass over volume, 0.639 divided by 317. And that says 0.00202 grams per cubic centimeter, which is interesting because, let me rewrite it on this page, the actual density of our gas is 0.0018. And then the one that I did in the lab we measured it to be 0.00202. So really, that's pretty good. I got pretty close there. Because if we're going to use significant digits, we should put a 0 there. So you can see 0.00180, 0.00202. Not too bad. Not too bad in terms of our measurements. And again, it's also important to note, you will see it in the book written in scientific notation. So basically, we're going to take this decimal and move it 1, 2, 3 times to get 1.8 times 10 to the negative 3. And this one, if we did the same thing, we would have 2.02 times 10 to the negative 3. And that is that.